We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone.
We have ignition.
हम ज़मीन के रहने वालों की तरफ से आपको खुश आमदीद कहते हैं।
Hola y saludos a todos.
Greetings and friendly wishes to all who may encounter this Voyager and receive this message.
Hello.
We step into the universe with humility and hope.
Hello from the children, from the children of planet Earth. Hello. Hello from the children of planet Earth.
Hello, greetings mga ka-spacers natin out there. Magandang araw po sa inyong lahat from Luzon, Visayas, and Mindanao. This is your ka-spacer and Space Commander Professor Jun Cajigal. And I would like to welcome everybody to this online lecture about stars. So before we proceed into the details of stars, so mga ka-spacers, please like, share, and subscribe so that we could reach more people, especially the students out there, so that they would be engaged in the sciences. So again, mga ka-spacers, like, share, and subscribe. So ano pang hinihintay natin? And let us learn about stars. Hello, greetings mga ka-spacers natin out there. Welcome to this online lecture, and for today's topic, we shall study stars. Now, what are stars anyway? Now, basically stars, they are objects that heat and light the planets in a particular system. A star is a ball of plasma held together by its own gravity, like our sun. Our sun is a star basically, and in terms of composition, our sun is composed mostly of hydrogen and helium. So stars also basically are the same, they are made up of hydrogen and helium. And nuclear reactions occur in stars like our own sun, wherein hydrogen fuses to form helium, and that is what we call nuclear fusion. And the energy from nuclear fusion, much like our own sun, is released in the form of electromagnetic radiation. So come to think of it, mga ka-spacers, our sun and all the stars in the universe, they are basically nuclear fusion reactors, wherein in the interior of the sun and all the stars out there, hydrogen fuses to form helium, and that's nuclear fusion. And in the process of this nuclear fusion, the sun and even all the stars out there, they release energy from these nuclear reactions in the form of electromagnetic radiation. So isn't that fascinating indeed? Now let's talk about now the characteristics of stars. Now one thing to consider is the distance of stars. Now stars are really incredibly far. Ang lalayo ng mga yan. You cannot just imagine the distance of those stars. And we don't make use of kilometers or miles in measuring their distances. We make use of the term light year. Now what is a light year? A light year is basically the distance in which a ray of light would travel in 1 year. And that is about 6 trillion miles. And we know that light travels at about 186,000 miles per second. So that is a light year, and that is used in measuring the distances of stars, because stars are really incredibly far. Now, another thing to consider in our study of stars would be its magnitude or brightness. Now, when we speak of magnitude, magnitude is the measure of brightness of celestial objects, and magnitude can be either apparent or absolute. Now, when we say apparent magnitude, this refers to how bright a star appears to be from Earth. And when we say absolute magnitude or luminosity, that refers to how bright a star actually is. Now, aside from distance and magnitude, another thing to consider in our study of stars would be its temperature and color. In fact, mga ka-spacers, stars are classified based on their color spectra, meaning that the elements that they absorb, and also their temperature. In fact, mga ka-spacers, there are 7 main types of stars. Now, in order of their decreasing temperatures, we have the following: Class O, Class B, Class A, Class F, Class G, Class K, and M stars. Now, the Class O and Class B stars are uncommon but very bright. And the Class M stars are common but dim. And there is an easy mnemonic for remembering this classification of stars. So we have O, be a fine girl or guy, kiss me. And did you know, mga ka-spacers, that our sun is a Class G star? So mga ka-spacers, that's how stars are classified in terms of temperature and color. So a star's color is determined by the temperature of the star's surface. Relatively cold stars are red, warmer stars are orange or yellow, and extremely hot stars are blue or bluish white. Color, mga ka-spacers, is the most common way to classify stars. And the diagram here shows the classification system, mga ka-spacers. The class of a star is given by a letter, and each letter corresponds to a color and also a range of temperatures. And for most stars, mga ka-spacers, the surface temperature is also related to size. So everybody kindly take a look at this illustration. Now, bigger stars produces more energy, so their surfaces are hotter. These stars tend towards bluish white like the Class O and the Class B stars. Smaller stars produces less energy, so their surfaces are less hot, so they tend to be yellowish like our own sun. So mga ka-spacers, now one of the most important tools in our study of stars is the so-called Hertzsprung-Russell diagram, developed independently in the early 1900s by Ejnar Hertzsprung and Henry Norris Russell. It plots the temperature of stars against their luminosity, or the color of stars or spectral type against their absolute magnitude, as you could see in this diagram. So this is the so-called Hertzsprung-Russell diagram. Now, depending on the initial mass, every star goes through specific evolutionary stages dictated by its internal structure and how it produces energy. Each stage corresponds to a change in the temperature and luminosity of the star, which can be seen to move to different regions on our Hertzsprung-Russell diagram as it evolves. This reveals the true power of the Hertzsprung-Russell diagram, and astronomers can know a star's internal structure and the evolutionary stage simply by determining its position in the diagram. So mga ka-spacers, everybody zoom in on our Hertzsprung-Russell diagram. And in this diagram, the three main regions or evolutionary stages of a star can be represented. And if you will notice that most stars are in the main sequence group. Now, the main sequence stars stretches from the upper left. Those are the hot, luminous stars. To the bottom right, those are the cool, faint stars. And if you will notice, the main sequence stars, they dominate the Hertzsprung-Russell diagram. It is here, mga ka-spacers, that stars spend about 90% of their lives burning hydrogen into helium in their cores. main sequence stars have a Morgan-Keenan luminosity class labeled V. And if you will notice in our Hertzsprung diagram, we also have the red giant and the supergiant stars luminosity classes 1 to 3, occupying the region above the main sequence stars. Now, they have a low surface temperature and high luminosities, which according to the Stefan Boltzmann law means that they have also a large radii. Stars enter this evolutionary stage once they have exhausted the hydrogen fuel in their cores and have started to burn helium and other heavier elements. And also in our Hertzsprung-Russell diagram, you will see here the white dwarf stars, luminosity class D. These are the final evolutionary stage of low to intermediate mass stars. And they are found in the bottom left of our Hertzsprung-Russell diagram. These stars are very hot but have low luminosities due to their small size. And our sun, mga ka-spacers, is found on the main sequence with a luminosity of 1 and a temperature of about 5,400 degrees Kelvin. So mga ka-spacers, that's our Hertzsprung-Russell diagram. And like what I have mentioned, most stars are in the so-called main sequence stars. Now, the main sequence stars, our sun included, is a major grouping of stars that forms a narrow band from the upper left to the lower right when plotted according to the luminosity and surface temperature on our Hertzsprung-Russell diagram. And everybody, mga ka-spacers, kindly take a look at this table that shows the class of the star, the spectral class, the temperature, and the color manifestation. So for class O stars, the temperature ranges from 20,000 degrees to 60,000 degrees Kelvin, and they manifest a bluish color. For class B stars, the temperature ranges from 10,000 degrees to 30,000 degrees Kelvin, and they manifest a bluish white color. Now for class A stars, the temperature of those stars ranges from 7,500 to 10,000 degrees Kelvin. So they manifest a whitish color. Now for class F, the temperature ranges from 6,000 to 7,000 degrees Kelvin, and they manifest a yellowish white color. For class G star, in which our sun is classified, the temperature ranges from 5,000 to 6,000 degrees Kelvin, and such stars, class G, like our own sun, they manifest a yellowish color. For class K stars, the temperature ranges from 3,500 to 5,000 degrees Kelvin, and they manifest an orange coloration. And finally, class M stars, they exhibit temperatures ranging from 2,000 to 3,500 degrees Kelvin, and they manifest a reddish coloration. Alright, so I hope everything is clear about the classification of stars. So before we continue with our next topic on the life cycle of stars, let's watch this short video about how stars are classified. Alright mga spacers, let's watch this.
Hello everyone and welcome to our universe. Today we're talking all about stars. So in this video you're going to learn a lot of things about stars. we're going to be asking questions about stars. For example, what exactly is a star? What is a star made of? Which is the closest star to us? And many more. So let's jump right in and talk all about stars. So what exactly is a star? A star is a huge sphere of very hot glowing gas. Stars produce their own light and energy by a process called nuclear fusion. This happens when lighter elements are forced to become something heavier. For example, hydrogen turning into helium. When this happens, a tremendous amount of energy is created, causing the star to heat up and shine. Stars come in a variety of sizes and colours. Our Sun is an average-sized yellowish star. Stars which are smaller than our Sun are mostly reddish, and larger stars are mostly blue. And also the colour of the star indicates the temperature as well. So what exactly are stars made of? Stars are basically made of very hot gas. This gas is mostly hydrogen and helium, which are the two lightest elements. Stars shine by burning hydrogen into helium in their cores, and later in their lives create heavier elements. Most stars have small amounts of heavier elements, like carbon, nitrogen, oxygen, and iron. After a star runs out of fuel, it ejects much of its material back into space, recycling this material into the new generation of stars. And these new stars are being formed from this material. So how many stars can we see in the night sky? The number of stars that you can see in a night sky, basically a moonless night sky, and also in a dark area, basically away from city lights, is about 2,000. Basically, the darker the sky, the more stars you can see. So astronomers hate light pollution. And if you have a moon in the night sky, this reduces the number of stars that we can see. So how many stars are there? Well, to be honest, no one quite knows exactly how many stars there are in the universe, but we can give it a good guess. There are so many stars, billions and billions of them, that it's not actually possible to count them. Our own galaxy, the Milky Way, has several 100 billion stars, and best estimations say that it's at least over 100 billion. And also there are billions of other galaxies in the observable universe, which have less or the same or maybe even more stars in their galaxies. So what exactly is the closest star to us? Well, the closest star is of course the Sun, at 93 million miles away. But that's a bit of a cheat, so let's talk about the next nearest star. So the next nearest star is a star called Proxima Century, and it lies at a distance of 4.3 light years. So to put it in comparison, a car travelling at 60 miles per hour would take more than 48 million years to reach the closest star. Proxima Century is actually part of a triple star system, which also includes the stars of Alpha Centauri A and B. Proxima Centauri is a small red star, and it is about 1/10 the size of our Sun, so you can't quite see it in the nighttime sky. You need a very big telescope to observe this dim star. So is the Sun the largest star? Although the star is massive compared to Earth, and looks massive compared to any other star, there are actually many stars that are much larger. The Sun appears so large compared to the other stars because it's just simply much closer than any other star in the night sky. The Sun is just simply an average sized star, with an average brightness and an average mass. And for an example, I'm going to give you a list of some of the largest stars in our galaxy. So the first one is called Deneb, and this is about 140 times the size of our Sun. Antares, which is about 530 times the size of our Sun. Betelgeuse, which is in the constellation of Orion, is 900 times the size of our Sun. And Mu Cephei is about 1,500 times the size of our Sun. So one of the most common questions in all of astronomy is, will we ever travel to the stars? Well, travelling to the stars is very difficult, because they're basically so far away. The nearest star is 4.3 light years away, which in our technological age is impossible. It would take nearly 4.5 years to get there, and that's just the closest star. It is always possible that sometime in the future, people will find a way to travel to the stars, but right now, we just do not have the technology.
Alright mga ka-spacers, so isn't that fascinating about how stars are classified? So remember mga ka-spacers, our Sun as a star is classified as a Class G star. Alright, so at this point, let us now study the life cycle of stars. Now, stars, just like us, they also undergo a life cycle. And stars begin their lives as clouds of dust and gas. And we call that mga ka-spacers a nebula. And gravity causes the nebula to contract. Then eventually, matter in the gas cloud begins to condense into a dense region called a protostar, and that will be the beginning of our own Sun. The protostar continues to condense, it heats up, eventually reaches a critical mass, and nuclear fusion begins wherein hydrogen fuses to form helium. And eventually the star begins its main sequence phase. And most stars spend their lives in this phase, as I have mentioned during the explanation of the Hertzsprung-Russell diagram. Alright mga ka-spacers, so let's take a look at this diagram showing the life cycle of a star. Now, as I have mentioned earlier, a star originates from a large cloud of gas called a nebula. The temperature in the cloud is low enough for the synthesis of molecules. Then eventually, when the gas particles in the molecular cloud runs into each other, heat energy is produced. This results in the formation of a warm clump of molecules referred to as a protostar. The creation mga ka-spacers of protostars can be seen through infrared vision, as the protostars are warmer than other materials in the molecular cloud or nebula. Then eventually the star undergoes a T-Tauri phase. A T-Tauri star begins when materials stop falling into the protostar and releases a tremendous amount of energy. The mean temperature of the T-Tauri star isn't enough to support nuclear fusion at its core. The T-Tauri star lasts for about 100 million years mga ka-spacers, following which it enters the most extended phase in the development of the so-called the main sequence phase. Now, the main sequence phase is the stage in the development where the core temperature reaches the point for fusion to commence. In this process, the protons of hydrogen are converted into atoms of helium, and that's nuclear fusion mga ka-spacers. This reaction is exothermic. It gives off more heat than it requires. So the core of main sequence stars releases a tremendous amount of energy. And our star at this point belongs to this main sequence phase. So mga ka-spacers, once a star reaches its main sequence phase, The next question is, how long will that star burn its hydrogen fuel to sustain nuclear fusion? Or how long will the star last, or its lifespan? Now, the lifespan of a star will depend on its size. So take note mga ka-spacers, the lifespan of a star depends on its size. Very large, massive stars like Class O and Class B stars, they burn their hydrogen fuel much faster than smaller stars like our own sun, which is a Class G star. Their main sequence may last only for a few 100,000 years mga ka-spacers, so very short lifespan. Smaller stars will live for billions of years like our own sun because they burn their fuel much more slowly. And eventually, the star's fuel will begin to run out. Like our own sun, mga ka-spacers, our sun has been around for about 4 or 5 billion years. And since it is a Class G star, it will continue to burn hydrogen for another 4 billion years. So mga ka-spacers, stars are not infinite. Eventually, their hydrogen fuel would run out. Now, what happens to a star when its hydrogen fuel runs out or becomes depleted? Now, when all of the star's hydrogen fuel is depleted, it will expand into what is known as a red giant. But again, it will depend on the size of the star. Now, very massive stars like those of Class O and Class B, they will become red supergiants. This phase will last until the star exhausts its remaining fuel. And at this point, the star will collapse. So mga ka-spacers, for very massive stars, like the Class O and the Class B stars, once their hydrogen fuel is depleted, those very massive stars will expand into what is known as a red supergiant. Those massive stars like Class O and Class B stars. Now, what about average size stars like our own sun? So our own sun, once its hydrogen fuel is depleted, our sun will expand into a red supergiant. And for most average stars like our own sun, it blows away their outer atmospheres and eventually forms a planetary nebula. Their outer cores will remain behind and burn as a white dwarf until they cool down. So that's the end of our star's life. It will end as a white dwarf, and eventually what will be left is a dark ball of matter known as a black dwarf. So that is the end for most average size stars like our own sun. So mga ka-spacers, that is how our sun will end its life. Eventually, once the hydrogen fuel becomes depleted, average size stars like our own sun will end as a white dwarf and eventually will turn into a black dwarf. Now, what about very massive stars like Class O and Class B stars? How do they end their lives? Now, very massive stars, they will collapse and eventually will trigger a violent explosion known as a supernova explosion. Now, if the remaining mass of the very massive star is about 1.4 times that of our sun, the core is unable to support itself and will collapse further into what is called a neutron neutron star. So mga ka-spacers, kindly take a look at this diagram. So for average size stars like our own sun, once their hydrogen fuel becomes depleted, average size stars like our own sun will begin to expand into what we call as a red giant star and will end their lives eventually as a white dwarf and into a black dwarf. Now for very massive stars like class O and class B stars, once their hydrogen fuel becomes depleted, they will expand into what we call as a red supergiant star, and eventually that will trigger a violent explosion known as a supernova explosion. And eventually the explosion of the supernova will turn that star, that very massive star, into a neutron star. Now wait mga ka-spacers, hold your horses. There's another twist into the life cycle of very massive stars like those of class O and class A stars. Now after the supernova explosion, those very massive stars will eventually end their lives as a neutron star. Now here's the twist mga ka-spacers. Now the mass inside the star will be compressed so tightly that its atoms are compacted into a shell of neutrons. Now if the remaining mass of the star is more than about 3 times that of the sun, it will collapse so completely that it will literally disappear from the universe. And what is left is an intense region of gravity, which we now call as a black hole. Now, isn't that fascinating mga ka-spacers regarding the formation of black holes? Now, everybody kindly take a look at this diagram. So again, for average size stars like our own sun will end its life as a white dwarf and eventually into a black dwarf. But for very massive stars like those of class O and class B, once their hydrogen fuel becomes depleted, those very massive stars will expand as a red supergiant star, and that will trigger a violent explosion known as a supernova explosion. After the supernova explosion, the star will either turn into a neutron star or a black hole. So isn't that fascinating mga ka-spacers? Now at this point, let's watch this short video about the life cycle of stars. Alright, let's watch this!
Way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the center of that cloud, it gets denser and denser, it gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out, and at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is, as the outer layers of the star get farther and farther from the middle, the force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object. It's dead. There's no nuclear fusion going on it anymore. It's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang, the outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun, but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star billions of years ago, before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually, I think that ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
Alright mga ka-spacers, so isn't that fascinating about the life cycle of stars? So I hope you have learned a lot through that video about the life cycle of stars. Now, before we end with this online lecture about stars, I guess it is also important for us to mention about pulsars. Now, what is a pulsar? Now, a pulsar is a highly magnetized rotating neutron star. So we mentioned neutron stars a while ago. Now, pulsars are highly magnetized rotating neutron stars that emit a beam of electromagnetic radiation, and this radiation, mga ka-spacers, can only be observed when the beam of emissions is pointing towards the Earth. This is called the lighthouse effect, mga ka-spacers, and this would give rise to the pulse nature that gives pulsars their name, and this is detected through radio astronomy. So isn't that fascinating indeed about pulsars? So I guess that's about it for our online lecture about stars. Now we will have another episode or video about black holes and galaxies. So I hope you have learned a lot about stars. So again mga ka-spacers, please like, share, and subscribe this video so that we could reach more people, especially the students out there, so that they would be inspired and they would be engaged in the sciences. So I guess that's about it mga ka-spacers. This is your ka-spacer and Space Commander Professor Jun Cajigal saying, live long and prosper. And always remember mga ka-spacers to keep your space. So long for now and see you in my next video. Bye-bye!
8, 7, 6, 5, 4, 3, 2, 1. We have ignition.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone.